Now we turn Cosmos SDK architecture into something real. You'll build a small custom module end-to-end. Messages, keeper logic, state changes, queries, CLI commands, and app wiring. By the end, the module won't just exist. It will run. You already have the foundation: the Cosmos ecosystem, Comet BFT, ABCI, chain setup, and the core SDK pieces, modules, keepers, stores, and messages. Now we'll turn that architecture into code by building a module that owns state, validates input, runs keeper logic, and answers queries. Our concrete target is a small but complete text or registry module. Accounts will submit transactions to create, update, or delete named records. The keeper will validate those requests and write record data into the module's own key value store. Other clients can read that state through gRPC queries, including lookup by name and listing records. Finally, CLI commands wrap both workflows, so users can interact with the module without writing custom code. A Cosmos SDK module has 3 clean layers plus 1 source of truth. The types package defines the public contract: messages, queries, errors, keys, params, and generated prototypes. The keeper holds state access and business rules, including service implementations. The module package wires everything into the app, including genesis and registrations. Proto definitions drive the generated messages and gRPC services, so keep them central and consistent. Before writing message handlers, decide exactly what state exists and how it will be addressed. A record is more than its fields. Its key determines how cheaply you can find it later. A prefix plus a stable name gives deterministic lookup. If you also need queries by owner or time, design separate indexes up front. Store keys become part of your module's contract, so changing them later usually requires a migration. Protobuf is the module's source of truth. In tx.proto, messages such as misjustCreateRecord, misjustDateRecord, and misjustDeleteRecord define what users can do. In query.proto, request and response types define what clients can read. From those definitions, the SDK generates Go types, gRPC services, CLI commands, and client interfaces. Signer annotations tell the transaction system who must authorize a message. After any proto change, regenerate code so every layer stays aligned. Messages are the public commands that move state from one valid condition to the next. A create message carries the new record data and fails if the name already exists. An update message targets an existing record, but only the owner should be allowed to change it. A delete message removes state only after authorization passes. Keep messages small and explicit, so validation, permission checks, and keeper execution stay easy to reason about. Validation works best as 2 gates. First, stateless message validation rejects inputs that are wrong by themselves: missing fields, bad addresses, excessive length, or malformed names. Then keeper logic checks facts that require the store, such as whether a record exists, whether a name is already taken, or whether the signer owns it. Never rely only on client-side checks because users can submit transactions directly. Return module-specific errors so failures stay predictable. The keeper is the module's gatekeeper for state. Message and query logic should not build keys, serialize values, or write directly to the store. Instead, they call narrow keeper methods such as setRecord, getRecord, hasRecord, and removeRecord. Those methods hide storage details and enforce rules at the boundary, including unique names and owner-only updates. This keeps business logic consistent, testable, and much harder to bypass. The message server is where a valid transaction becomes application state. Each handler, such as createRecord, accepts context and a typed message, validates the signer, checks current state through the keeper, and then calls keeper methods to mutate data. It should not write directly to the store. After the change, emit events or typed events so indexers, explorers, and clients can observe what happened. Then return a typed response back to the pipeline. Once your module builds on its own, app.go is where it joins the chain runtime. Create and mount the store key, then instantiate the keeper with every dependency it needs. Register the module with the module manager and service configurator so messages, queries, and services resolve correctly. Finally, wire genesis order, begin or end blockers, and export paths. A missing registration can still compile cleanly, but fail at runtime. Queries are the read side of your module. They let explorers, CLI users, relayers, and apps ask for state without changing it. A record query supports direct lookup by name, while list records supports iteration with pagination. The gRPC query server calls keeper read methods, which access the KV store and return typed responses. That typed contract keeps clients stable across REST gateways, SDKs, and future module upgrades. The CLI makes the module's contract usable. A transaction command turns user input into a message, signs it, and broadcasts it, such as creating or updating a record. A query command does not change state. It calls the module's query service and returns data, such as showing one record or listing many. The key discipline is consistency. Command names should match module concepts, and flags for node, chain ID, gas, fees, output, and pagination should behave predictably. Execution is a handoff chain. The CLI builds a module message, wraps it in a transaction, and signs it. Comet BetFT orders that transaction into a proposed block, then finalizes it through ABCI++. Base app receives the finalized block and routes each message to the correct module message server. From there, keeper logic validates permissions, changes state, and emits events. Once the block commits, those writes become durable, queryable chain state. You now have the full module pattern. Define contracts and types, enforce state changes through keeper logic and message servers, expose queries and CLI commands, and wire everything into the app. That is the foundation production chains build on. Next, we'll strengthen it with review, documentation, and testing.